Hi, I'm recording this video in New Bern, North Carolina on my boat, and it's really cold tonight and my heat is not working properly. So I decided to keep busy and put this together, and it's something that has been developing all along in all my presentations, but I thought I would show you how you begin with an algorithm and how it basically spells out the answer to the problem. So one has to qualify what one means by proving a conjecture with an algorithm, because technically it's not enough. It also requires something else. I found this quote right away on khanacademy.org. Actually, the first thing I Googled, the only way to prove the correctness of an algorithm over all possible inputs is by reasoning formally or mathematically about it. One form of reasoning is a proof by induction, a technique that's also used by mathematicians to prove properties of numerical sequences. So this applies perfectly, and I have used induction in a lot of my presentations, uh, and I will do it again in this one, but I just want to begin with the algorithm. Here we have the complete algorithm. It's very simple. I've written this in Python code here, and there are three possible operations. So to understand it, one might want to look at the function. So in the function we have three conditions, and these can be considered congruence tests, and they correspond with a series of numbers with a specific interval and a specific starting point, and I'll show those in a subsequent slide. But for shorthand, I'm using A, B, and C, and I'm also using that in the code just as a marker, the input A, B, and C and the output A, B, and C. It's actually not part of the algorithm per se. The algorithm per se is the test, the congruence test, and the operation. Congruence test, operation, and then we don't need the congruence test in the else case because it's taken care of. It's got to be one of these three. Now, if we, so there we see the A, B, C correspond with those in the function. And just like I said, the input ABC and the output ABC. Now, we're going to execute the code, and this is recorded, and you'll hear some background noise while this happens. So the output, or the generated numbers, and excuse this at the top, the generated numbers are first the input numbers, which are the sequential or consecutive odd numbers. Their congruences, as previously mentioned, ABC, and the output numbers and their congruences, ABC. So just by the way, if you have Python output with comma separators, you can easily import them into Excel. You just name the text file with an CSV extension, and the comma delimiters will produce the columns in Excel. Once the generated numbers are in Excel, we see what's on the left. And so we see in the input column the consecutive odd numbers, and in the output column we see something which appears to be haphazard and erratic, but believe me, it's not. It's very simple to see some structure and repetition in this, the most obvious being that every odd integer is present with an interval of 4 between them. So we see that here all the way down, and this will continue for infinity. So this is very important. By and of itself, this shows that every odd integer belongs to a sequence. Obviously, if each sequence follows the same recurrence pattern, and we know the initial sequences are all convergent, then all the ones that follow must be convergent as well. That is an empirical argument, and we'll try to tie that down a little bit more as we continue. On the out, let's just have a look at what the A, B, and C mean. You'll notice that BACA repeats itself for the consecutive odd integers, and A is begins with the first number that's congruent. A is 3, and then every number that follows with an interval of 4 is also congruent A. B begins with 1, and every number that's 8 apart is congruent B, or has the congruence B, and C is 5, and every following number 8 apart. So just to make it clear what really A, B, and C are, remembering n is odd, so if m plus 1 is evenly divisible by 4, the number belongs to A. If m minus 1 is evenly divisible by 8, the number belongs to B. If m minus 1 is evenly divisible by 4, the number belongs to C. And you will not get any overlap between A, B, and C if you consider them to be sets. They are entirely disjoint. There's no overlap between these sets at all. Each number is a unique element of one set. So if we take a deeper dive into the output, we see that all the numbers are paired, and except for those divisible by 3. And you just have to turn that around in your mind and realize that it's actually 2 inputs and 1 output. So there's only one 7, there's only one 11, there's only one 13, but there's 2 inputs for each of those numbers. And the interesting thing is that C is always one of those inputs. So for 7 we have 2 inputs, 9 and 29. So 9 is congruent B, and 29 is congruent C. I should really just say case. So let me just change that to case from now on. So in the case of 11, we have case A and case C, 7 and 45. And then for 13, we have case B and case C. So that actually covers it. There's only 2 possibilities, except for those numbers divisible by 3. all the odd numbers have two inputs, and one of them is always C, and the other is either A or B. And what that means is we're looking right at how sequences converge. That's exactly how sequences converge. So the sequence, let's pretend there's a sequence that begins with 9, and let's pretend there's a sequence that begins with 29. And they both converge on 7, and 1, yeah, so in every case, C is one of those convergent numbers. And the reason I say let's suppose it begins with 9 or 29 is because there is no beginning to any of these sequences, and that's one of the fallacies that it appears mathematicians have fallen foul of. It's a fallacy. So, these sequences begin at any indeterminate point you want to choose, or I mean, you can't say they begin at any particular point in the number line. They begin at infinity, wherever infinity is, and they converge onto 1. And they converge onto 1 by this mechanism, which I'm showing here, of A and C, or B and C, converging on an output number that could be A or B or C. The problem with the multiples of 3 is it's not a problem. It's that the input is always C, and the output can be case A or B or C. But the beautiful thing is we don't have to think about convergence for the multiples of 3, because they don't exist in the conventional conjecture. As we know, when we multiply a number by 3 and add 1, it cannot be a divisor. It cannot be divisible by 3, evenly divisible by 3. So we can actually just put that to one side. We don't need to prove their convergence, but we can. But I'm not going to go further into that now. What I'm going to go into is why convergence using the operation C, or case C, is not apparent when using even-odd sequences. So that's what I'm going to get into in the next slide. So here, and I'll just read this, when you sort by output, you see that all integers must be convergently paired, except for multiples of 3. So we covered this. The convergent pairing must be without exception, with inputs being A and C or B and C. So Congruence C is what I've previously termed the third rail in a previous presentation. The third rail of the conjecture, because it's not apparent in even-odd sequences. And that is because the odd numbers that are the result of n-1 times a quarter are replaced by two even numbers. So this is really important. If we look at this odd-only sequence beginning with 29, we calculate it as 29 minus 1 times 0.25, and that gives us 7. And you will never see that number. That number, I don't even want to call it an intermediate number, but from an even-odd perspective, you might think of it as an intermediate number. You never see that number. What you see is 11. So this is the conventional function in its rather convoluted fashion. It multiplies 29 by 3 and adds 1, and then divides it 3 times in this case. And you see there is no 7 to be seen anywhere. And what you see at the end is 11. So this recursive operation produces 11, and my odd only function produces 11 as well, but it's in the following step where 7 is congruence A, and then you get plus 1, 8, multiplied by 1.5, which is 12, minus 1, which is 11. So they both end up at exactly the same point, but you do not see the convergence point of 7 in the even-odd sequence. You just see it going from 29 to 11, and that must produce a very, very strange fractional ratio that that baffles mathematicians and which they believe to be very complicated. It's not. There's a hidden sequence there. We're at the end, so I'm going to wrap up the conclusion by induction and say that the algorithm I presented discloses that all odd integers are input-output pairs. And if every output not evenly divisible by 3 has 2 inputs, there cannot be a case where an output integer is the beginning of an infinitely divergent sequence that does not end in 1. We know from the basis cases that ascending the number line, all sequences are convergent. The basis cases are the ones I show here, strictly the very first one, input 1, output 1, and then, but we have this essential second case of input 5, output 1, which is this operation C. And then in each of the following cases, we see the same thing, that operation A or operation B is complemented by operation C in each case. And this is really the sum of it. There's nothing else to say. Either you get it or you do not. Thank you.